Okay, so today we will continue with some now more discussion about details of DLA. Actually, one question was discussed last time, so I thought it is interesting to follow it up. Actually, I was thinking about some sort of behavior in DLL. Then I thought, okay, let us make it an example and then we will discuss it in the lecture. It is always good to discuss something that is not trivial and straightforward. Okay, now this is that structure of multi-phase generation, right, from a clock. So I have an input clock with phase phi I. I want to generate different phases of this clock, phi 1 to phi n, and therefore I make this loop, right? This was one of the points that we discussed last time. So now suppose if I, and then at that time I ignore the effect of phi I as an input to this module, right? And now the question one of the students asked was, okay, so if we consider phi I anyway is an input, right? And then we assume that it has its own dynamics, therefore we change it. So now what will be the effect? Okay, so then let us write the entire transfer function. Okay, so phi out will be 2 pi upon t, k delay element into n, because we have now n, therefore there will be n, the delay of one element multiplied by n, and then hs, which will be the transfer function of phase detector and loop filter, phi I minus phi out plus phi I. And this essentially, this 2 pi upon THS will give us VCTL. Okay. So this is clear. Very interesting. Now if you solve this, you will reach to that phi out is equal to phi s. Very interesting. No dynamics. Instantaneously it will answer to the change in the input phase. Let's see how it works. Why we reach to this some sort of anomalous behavior. Suppose in this scheme, I change an abrupt change in our input phase. Okay? Now input phase changes instantaneously by some amount. I have considered my delay elements don't have any latency. If you remember from last to last lecture. If you remember here, if I have any change in input phase, that will be directly transferred to the output phase. Okay, this was the characteristic of delay element, right? If I change my input phase, my output phase also will change by the same value because delay element is giving a constant delay. Now, what was the small point which usually is considered in all DLL analysis? I checked many textbooks. Actually, what they consider, they assume the delay element is an element which responds instantaneously, but actually it doesn't. And all the entire analysis is based on this. If it can respond instantaneously, then yes, phi out will be equal to phi in. Phi, I have a delay element. There is no latency in this delay element. I change phase here, output will change by the same value. Therefore, it is expected to have this. It makes sense. If I have a delay element which responds to the input phase instantaneously, then I can have a DLL without any delay. Right? This is absolutely correct. Of course, I have done one assumption. If you write the equations, actually it will be a transfer function in which denominator and numerator are equal. Therefore, I just cancel both of them. No, there is. This has its own filter. This is loop filter. There won't be. See what happens. Let us give an example. Suppose input phase changes by just 1 degree. Okay, but instantaneously. 1 degree. Delay element has 0 latency. So output phase can change by 1 degree. Therefore, error, instantaneous error is 0. Therefore, filter doesn't respond. Having a filter or not having a filter doesn't have any effect because filter doesn't sense any change in the input phase. differential phase. There is no error, instantaneous error, which is generated at the input of phase detector. There is no stimulus to the filter, right? Therefore, its output will remain constant. Exactly. No. There is no information. That is the point. The entire information is grabbed here in delay element. You have a phase at the input. Delay element responds exactly with zero delay to that, which is not correct. But this is the assumption. And therefore, it leads to this sort of anomalous behavior. See, you have 1 degree change here. You get it at 0 time here. Then what this does? Nothing. Exactly. Now, this analysis is based on considering we get it in 0 time. Therefore, we don't have any phase shift, any phase difference, or any phase error at the input of phase detector. To be providing, yes, VCTL provides delay. In fact, it controls the delay through delay element. If this delay is constant, phase shift through this cascade of delay elements is constant. So, if VCTL remains constant, means error is 0, therefore phase shift is constant, right? Therefore, it doesn't change anything. But in that case, we didn't have 2 inputs to the loop. Look, here the difference is you have 2 inputs to the loop. One goes to delay element, one goes directly to phase detector. There we didn't have this problem because we have just 1 input and then the entire feed-forward path was here after loop filter. But here now actually we have 2 paths, right? Yes. Therefore, it has delay. It has latency. But now it's very interesting. If we have latency, then how we can model it? Now it will be actually not exactly linear. Okay, so this is actually, that's why I put a question mark. Be careful, this is the 0 state response, not a steady state 0 input response. Okay, do you know what is the difference between 0 state and 0 input? If you have a system, okay, just a linear system. This linear system has some sort of state equations, okay. So these state equations define relation between output, state variables and input, okay. If I don't have any input to that system, but somehow because of some problems, that system is not in an equilibrium condition. The transient performance it shows, it is called a 0 input response. There is no input, but still it is going to show some dynamics. A simple, for example, you have an RLC circuit. I just use, for example, a magnetic coupling. I bring some magnet or some coil close to the coil in RLC circuit and then I take it out. And I assume my time starts when I take it out. Therefore, I have inducted some magnetic flux in the coil. Now what will happen? Because of that, now there is some energy there. That energy will get dissipated in the resistance of RLC circuit. Therefore, there will be a transient associated with it. But effectively, I don't have any input current to the RLC circuit or input voltage, depending whether it is series or parallel. So effectively, this is called a 0 input response. We have also 0 state response. I have an RLC circuit and it doesn't have any initial energy. Therefore, it will remain as it is in an equilibrium if I don't apply any input. As soon as if I apply an input, then I will get an output. And the linear relation between output and input is quite linear. This is a linear expression which is explained by HS. So transfer function of the system has a transfer function only if we are talking about zero state response. Otherwise, a real system, even it is called linear, but actually it has two parts in his response. One is zero state response, which is modeled by HS, transfer function, and one is zero input response, which is because of n number of conditions, environmental conditions, and there are some energy in some parts of the circuit which needs some time to get dissipated or completely stored, and then it will be equilibrium state. Now here, what we consider, we write equations. We don't look at any initial state. We just look at HS, transfer function, not this HS. In fact, the entire transfer function of loop. Therefore, this is a zero state response, first of all. Therefore, if we want to write zero input response means if phi I is zero, phi I is actually a small signal. It means variation of phase is zero, but somehow VCTL is not the value that it should be. It should be, right? Therefore, I have some VCTL which is not zero. Finally, because this VCTL again is a small signal, I have some deviation, but this should decay and comes back to zero. So then for that actually this loop will perform properly. It won't give at all this instantaneous response, and then we will see. But as soon as I put this, then the zero state response will be instantaneous. Means that if there is nothing from outside, everything is already in equilibrium. If I suddenly change phi out also will change suddenly, and nothing else happens in the loop. Loop will remain in equilibrium as it is. However, delay element doesn't respond. Delay element actually is a delay element. It has its own latency. Therefore, phase doesn't change abruptly at the output as we expect at the input. So that is the very small, tricky confusion which happens. Now, how to avoid it and have a proper analysis? Suppose if I want to make a proper analysis by considering this delay. So, what we should do? Lock is locked and there is no transient associated with it. Means that VCTL has settled to a constant value. It depends on phase detector. After all, we have one single frequency, right? And if it locks, then these two phases will be equal. And then here we will get just 2 pi divided by for each phase. There are actually conditions, yeah. But here we have just a single frequency, right? And if phase detector has the entire span of phase shift, we would expect this loop to lock. And if VCTL can handle the amount of phase shift, right? If suppose sensitivity of delay element is too small, amount of delay which is given the entire span of working span of VCTL, linear range, is very small. Yes. If it is wide enough, then it's fine, because each one of them should generate a phase shift of 2 pi upon n, which is actually 2 pi upon n multiplied by t. That is the time delay it has to provide. If it can provide that time delay, then it will work. Okay, so now interestingly, if we want to write it, how it will be? Okay, so suppose if I have, I have a few things just I will write. If I have a delay element, this is a small signal, okay? So, a time domain means that if I have, for example, this is my input, considering some time reference, and now in some time it was supposed to continue in this way. Now, what I will do, for example, here I will apply an abrupt change So I will plot again. Abrupt change in the phase. So what does it mean? For example, I will here. Now from here it will change. Now it will continue. Now what will be the output? So this is Pi, which was supposed to be. Now here I have changed. Now suppose Pi has had, say, I would say that 90-degree phase delay. No, it is applied to the first one. There is a cascade of delay. First one, yes. Yeah. VCTL is common for all. This means that all of them will generate constant phase shift or constant delay between input and output, from input to output. Why delay should depend on input? Delay doesn't depend on input, right? So we assume that it doesn't. Therefore, if it doesn't, not assume, actually we want. We want so that it should work in such a way, delay should not depend on input. Therefore, it remains as it is, right? However, there is no instantaneous response from delay element. Either it is 1 or 2 or whatever. So that is the reason here, in this waveform, we don't get what we expect. See, what we write in equations and what we get from this, right? So, like here, I applied that changes. But what does it mean? Means that really I will see this change in the phase at the output. Now what happens here? This is input. Still this will generate 90-degree phase shift, right? Because VCD is not aware of instantaneous change. So if it was like before, then I would expect, okay, so then here, this goes high here. This would have come down here. Now input has changed, okay, so it will have its own delay, 90 degrees. So then it will continue. Okay, this is your entire one or one, just, yeah. Yeah, this is Phi out here. It's not PLL. It's just a single stage with CDE. It's not DLL. Just we have 90-degree phase shift. So when I write equations, I assume that always I'm looking at a given time stamp to the system. Therefore, if you look at this system, at this time, phase changes, right? But if you look at this was the expected output. How DLL can distinguish between these two? See, this part is common, right? What is the delay of this DLL? Here phase has changed. But In fact, phase, has changed here. But effect of this change at this point appears here, right? So if this point A, corresponding point will be here. So effect of phase change appears after this delay. Therefore, there is a delay associated with delay element. Therefore, when we write phi out s is equal to phi in s plus delta phi, we assume that, what does it mean? It means that always, at any time, phi out is able to follow phi in. But it is not correct because it will see phi in always after some delay. Therefore, if phi in changes at some time, it will take same delay to reach to phi out. Therefore, if I have an abrupt change in the phase, so this is phase, not amplitude. This is phase. This phase doesn't reach to output. Output doesn't see it unless there is a time delay, and then output will follow it. Effectively, even for phase also, or variation or change in the phase also will have this time, this latency. And that's why effectively it is not able to respond instantaneously. Therefore, phase also has its own delay. Then how we can model it? Then is it correct to say that phi out is phi out t, phi in t minus some time delay, which is time delay of delay element? We are actually saying. What do you mean from inherent delay? Actually, that is the point. This is a signal, right? But we are looking at the phase of the signal. If you change phase of the signal at time equal to 0, when do you see this change at the output? Same delay. Same delay, ignoring any other thing. Just it's a delay element with the delay of t. Then what does it mean? If I can write this, then means that in Laplace transform, actually this will be phi out s will be e to the power std into phi n s. Okay, so now to see how this behaves, so there are two things. One thing will be, okay, so then practically now how this loop behaves. Suppose if I apply, okay, therefore this phase still has not changed. This phase doesn't change abruptly. It will continue as it was. Therefore, here the one error will be generated. This error will change VCTL. And because of VCTL, now delay of this delay will change. So, and now this delay changes in such a way now, I had, for example, lagging, right? Now it will try to reduce VCTL. Suppose the slope is negative, okay? So this will increase VCTL, delay will reduce, and therefore now it will try to reduce the phase. So therefore, what would I expect? I would expect VCTL to increase, VCTL to go to negative values, and after several rounds, it should come back to 0. And this is completely nonlinear. Because as you see, even if I consider this simple relation, it is e to the power st. So this is effectively a nonlinear performance. So a few iterations and then again it will come back to 0. So it will come back to 0 but not at time equal to 0. Therefore this linear analysis is almost approximation, but it's okay. It happens only for this special case, which is an interesting case. No, its prediction is correct. It says that finally phi out and phi I will be equal, there will be no change in VCTL, means final value of VCTL still is 0. No, it doesn't. Actually, that term will get cancelled. If I look at the zero state response, so I can cancel those two. Therefore, there won't be any delay. But it predicts final values correctly. Final values say that there will be no change in these two phases will be exactly again same, and then VCTL will be as before. There won't be no change. Final value will be same as origin. So you will have something like this, something like this. It will. It will get cancelled. You just write it. Let it. Because when I wrote it, it got cancelled. We can check it. If it doesn't show, then it is good. Because still without considering this latency, it shows some latency. So equation will be like this. Phi out S into 1 plus 2 pi upon Tn K voltage control delay element Hs is equal to phi in S into 1 plus 2 pi upon Tn K VCDE Hs. You just transfer phi out to the left side, and right side you have phi on plus phi in into the transfer function. So you will get same value. See, original form, is it correct? Is phi out S is equal to K VCDE into N 2 pi upon T Hs into phi in S minus phi out S plus phi in S. Yeah. Phi is applied to both. You have two paths now. I'm talking about entire system. This is entire system. No, this is the entire system. Phi out. This is output of delay element, which is phi. No, that we derived, I ignored phi in. I removed it. What we derived last time, it was without phi into the input of delay. I ignored it. That was, I don't know your name. Yes? Suresh's question. So according to his question, I try like to see what are actually the small points in this analysis. Okay, but this is not the only architecture. Okay, now I will show you the architecture which actually gives the previous analysis. Okay, now suppose if I use another architecture. Suppose if I use for synchronization. Okay, this is second example. So for data and clock synchronization, this is a simple example. So I have just one delay element or some combination. You just consider it is a combination of delay elements or whatever. Just a module. Okay. Anyway, all of them have same VCTL. Okay. This doesn't change. But because it is not multi-phase clock generation purpose, that's why I combined them and just show it by one. Now here you have some data. You have a reference clock. And then you want to synchronize this data and clock with each other. And then assume that this data and clock has same frequency, because if frequencies are different, there will be different stories. Right now, just we don't want to enter. Just I want to show you different ways of making this loop. Now you have a data separately is coming, and then you have a reference, and then you have phi out. What it does, you have a data, you have a clock. You can just consider, for example, these two are two different clocks. Even it cannot be data, it can be a different clock. It has come from somewhere, this also has come from somewhere. We want to, this is, for example, a local signal, this is a global signal. We want to synchronize this local with that global, but same frequency. Okay, this is synchronization. Now here I have my reference, I have my data. So now here I write, okay, same thing, right? So I have a reference, I have an input. These two, right? Now here also I have two. Here it works, right? Suppose if I have this input, I have this reference. Finally, if this loop is type 1, then for phase, I will get these two to be equal, right? Therefore, this VCTL will change the phase of this signal, input signal phi I, in such a way it will get synchronized to the reference phase. Okay. So now here one of them is reference, one of them is data. Therefore, reference has its own constant cases. Therefore, your data may change instantaneously, or data or just local, or vice versa. For example, this might be constant, this will change instantaneously. Now here you can just consider one of them. Then the equation we wrote, then it is valid. Because now in this case you have just one input, and then if you write, you will get the same relation that we wrote last time. You will get a time constant for the loop, which is CTI upon KVCD. What does it say means that time constant of this loop to settle is a function of C upon I, which is expected. If C is less, I is more, I will have less delay, right? But at the same time, my filter will have a higher bandwidth, which is not good for the input jitter, for example. And then sensitivity of delay element. If I have a more sensitivity for delay element, loop will settle faster. It is also clear, because if sensitivity of the delay element is more, what does it mean? Means that if I have a small change in VCTL, I will get a larger change in the output phase. Therefore, it will settle to the change quickly. So, then this is correct. So, this is actually the main design parameter for DLL design. Okay, and usually we cannot control VCDE sensitivity, we can, but power constraints and other things limits us. Therefore, effectively C upon I is a very important design parameter. Okay. So now, giving just an example, suppose effectively, okay, so because time constant is this, therefore effectively like after 3 or 4 time constant, loop will settle. Suppose if I consider delay of 3 time constants, okay, therefore I will say that loop settling time equal to 3 tau. Okay, so this is example. Now suppose if I want to make it to be maximum 10 clock cycles, right? Therefore I want this 3 tau to be less than 10 clock cycles. So now interestingly, so I will just replace. So 3 into tau was C upon I. C upon I, KVCDE was here, right? 3 tau. This I want to be less than, okay, into T, less than 10 T. So this means that 10 KVCDE upon 3 should be greater than C upon I. This is important for the design. Now suppose for example if I have a delay element. This is one of the typical sensitivities we may get. 100 picosecond per volt. Then you will see how much value of C upon I is not as such good value. So this will be 10 to the power minus 10. This should be greater than C upon I. In fact, C upon I should be less than this value. What does it mean? C upon I should be less than almost, right? 3.3 into 10 to the power minus 10. Minus 9, sorry. Minus 9. No, minus 10, that is correct. It is 10 upon 3. Okay, so suppose, where is minus 12? 100 picosecond. Now, see, what are typical values, right? What is the typical, what value of C did you use for a charge bomb? Give me an example. What value of C and I did you use for charge bomb? $50 microampere, and C was 100 picofarad. Wow, it's too large. But anyway, you use 20 pico. Just I want to see what typical values, how this relation will be corrected. So this will be 50, 10 to the power minus 6. Yes, 20, 10 to the power minus 12. 50, 10 to the power minus 6. 0.4, 10 to the power minus 6. Now look at the order. Therefore, effective, even, latency of 10 clock cycles for DLL to lock. That's why the locking, actually this locking time sometimes reach to 50 clock cycles for DLL. Okay, but one thing important is usually the change in the phase is because of jitter. Therefore, the amount of change is not very large. Therefore, effectively, even it doesn't settle completely, it takes time. We always observe jitters, change. In fact, small changes in the input phase will appear always at the output because settling time for these changes is very long compared to the value of jitter. The time jitter takes to exist at the input. In fact, to be to be shown in the input signal. Like when you see a jitter means that your clock edge changes. Clock edge changes. Clock edge is very fast. For example, it can be 50 picosecond only. It can be maximum 100 picosecond only. And then just in this 50 picosecond, then you will see a change of 5 picosecond. It's too short, right? But even response to this, to settle, may take several clock cycles. Therefore, effectively, system is not able to follow it. So you will see jitter. Jitter will come into the system. So that's why this is a very important design parameter, and there is a latency with DLL. No, again, this depends on the loop, right? Loop filter. Because after all, what happens is, look at it this way. Suppose you have a reference clock of, say, 500 megahertz, okay? And then you have a loop bandwidth, okay? And loop bandwidth, say, is small. For example, it is 5 megahertz. So you have a bandwidth of plus minus 5 megahertz, around 500 megahertz. So this is the amount of jitter which will come inside. Means that if you have a jitter, because jitter will appear as phase noise. Therefore, if you have a phase noise within offset of 5 megahertz from 500 megahertz, this will come into the loop. The remaining part will get attenuated. Do you know about phase noise? Okay, briefly I will explain what happens. See, if you have an ideal oscillator, you connect it to a spectrum analyzer, what will you see? Suppose an ideal spectrum analyzer, ideal VCO. You will see just the peak, which is very large, and you will see almost infinite dB, right? Minus as the amplitude of the signal at other frequencies. So this is an ideal VCO. Now you have no VCO is ideal. So for example, you make a VCO and then there are some components which have noise. So for example, you bias VCO, right? VCO essentially is the oscillation around the bias point. Now you have the bias current source in the VCO. Okay. Now value of this bias current comes from a transistor, and transistor has flicker noise, which is the low frequency noise. So value of bias current is changing with time. Therefore, effectively, even if you have an ideal, very nice LC tank, which can give you a very, very nice frequency, that frequency alone is not the frequency that you will observe. You will also observe other things. The reason is that because you will have a nonlinear, of course it should not be ideal VCO, otherwise again we will come back to the same thing. So this is not an ideal VCO. Therefore it has a bandwidth. Means that if there are other frequencies in the signal also, this is not like that, it will filter them completely. Now this jitter, okay, now what this noise does, this noise changes bias point. And because it changes bias point, effectively it changes, this bias current is changing with time. This bias current is coming into the entire nonlinear part of VCO, right? So you have a nonlinear system, you have a time varying signal which is coming to that system. So this time varying signal, and you have the system which has look at it just a simply multiplier, okay? So therefore you have a low frequency signal, you have a main signal which is generating this main frequency. Now these two get multiplied. What does it mean? Means that the main frequency now is shifted between with a very small offset, right? Because this is a low frequency. So like if your frequency was 500 megahertz, now it might be 505 megahertz, it might be 495 megahertz. And this signal is noise, right? Therefore its variation is random. Therefore this change also will be random. Now if you look at the spectrum analyzer, you will see you have some shape like this, right? So it will be looking like this. If you look at power distribution, for example, it will be like this. So this is the main frequency. And then here you will see a spectrum. If this is narrower, then your phase noise is less. This is noise. The reason is it may be deterministic, but effectively due to different random noise sources in the circuit, this bandwidth has an RMS value, effective value. Now, what is jitter? Jitter actually is the same thing, right? If a frequency of a signal changes by a small amount, that's why this is called offset. So this is delta omega. For example, usually phase noise is mentioned as per the offset from a carrier. So now in the clock, in the digital systems, if you have a clock generator, you have a 5900 megahertz clock generator. So there are different reasons, even if you have a ring oscillator always doesn't have same delay at each cycle of oscillation. It's not. Because no physical system you can be found of which its performance is always same at all timestamps. So, effectively there are a lot of phenomena which change. So, in each cycle you will see a small change in the frequency of ring oscillator. So, how does it appear? It appears as a change in the age of the signal. So, edge of the clock has some changes. So, effectively it's not a sharp edge. Even if you look at it on a scope, you will see something blurry here. A scope even is not able to trigger because this is randomly changes. Therefore, oscope also will show you this type of ribbon here. So, this strip is actually jitter, right? Edge changes. What does it mean? It means that effectively phase or actually frequency is changing. So, this appears in the on the spectrum analyzer like this. Now, therefore, the question was how this DLL will respond to jitter. It depends on the bandwidth of the loop filter, because now you are applying a signal like this to the VLL. Now, if the bandwidth of DLL is 5 megahertz, then means that if there is a phase noise or jitter of which the components are plus minus 5 megahertz, suppose this is omega 0 plus 2 pi into 5 10 to the power 6, and this corresponds to omega 0 minus 2 pi into 5 into 10 to the power 6, and this is 2 pi into 5 into 10 to the power 8, 500 megahertz, considering just we are looking at main harmonic. So, therefore, bandwidth of DLL will determine how much jitter will come into the DLL from input signal, input clock, for example. So, that's why less bandwidth would be better. And less bandwidth means less I and more C. Therefore, it means that again same almost trade-off we had in PLL. Therefore, latency or response time of DLL will increase if its jitter performance improves. This is one of the reasons. Also, there is flicker noise associated with the components, thermal noise associated with the components. Temperature changes time to time. Temperature changes from one inverter to another inverter. Two inverters are not same. Threshold voltage changes. Even there is memory effect. If you run a ring oscillator for 10 minutes or if you run it for 100 minutes, you will see a different performance. So it depends, each node has some memory effect. It will rise, it will discharge. So it depends how many times you do this, and there are a lot of nonlinearity associated with this. Therefore, charge and discharge time and the speed is not always same also. Therefore, if you look at the average voltage at each node, that also changes with time. So there are many factors affects on this. LC oscillator is better if you want this. But first of all, LC oscillator will give you a sine wave. Therefore, then what you need to do, you need to amplify it by a preamplifier, then use for example, inverter, then it will give you logic levels. Therefore, you need to do some additional processing to get a square wave. And when you do this additional processing, therefore, these components again may add to the jitter, but VCO itself now will have a better performance. From this aspect, yes, it is better. But anyway, then you need to have this additional parts, and then also you need to have LC, proper LC with a good Q. Because if you don't have a good Q, then again that VCO will generate harmonics, which is not, that is okay. I mean, I would say that for digital applications, actually it's okay, it doesn't matter. But the point is, no, but if it is a differential VCO, it's okay. Because in a differential VCO, you don't have second harmonic, you will have third harmonic. In a 50% duty cycle of square wave also, you will have even odd harmonics only. Therefore, it's okay. You can convert it to the square. That's it. So, actually, this is used, some people use. Ring oscillator is used Actually, one of the methods is to use an external crystal and then use it as a reference clock and then use a PLL to generate. This is one of the very common methods for making a very nice digital clock. But for RF applications, yeah, LC oscillator is used. Yeah, in 0.18 micron, if you use say 5 stages, you will get easily 1 to 2 gigahertz. And that actually won't be exact square wave. If you reduce number of ring oscillator stages, instead of square wave, it will approach to a sine wave. Because it is just like now you have a set of amplifiers now. Then it will oscillate at a particular frequency. There are other methods also, like for example in the reference paper that I told you, they have used this configuration. Again, this is delay element, can be a combination of many delay elements. This is VCTL, all the small signal values. All these components are differential, therefore they have a differential input. So now they are generating, so this is a cascade, they are generating different differential outputs at different phases. So therefore this will give, for example, clock 0 plus, clock 0 minus, and this will be clock n minus 1 plus clock n minus 1 minus clock n plus, and this will be clock n minus. And now what I do is, so I don't plot, I have plotted outputs there, okay. Now they have again this phase detector and charge pump and filter. So what they give, everything is differential. They give clock 0 plus, clock 0 minus, clock n plus, clock n minus, and this will generate VCT. So now this is one way of doing that, and this is input, okay. So this is like clock input. So they generate n plus 1 phases, and they make the phase difference between first and last to be 0. Therefore they get effectively n phases. This is also one way of using this loop. And here again, if you notice, we have only one input. So again, the same analysis that we had is applicable. So it will be, its order will be depending on the order of this loop filter. If you use just one capacitor, then it will be first order. Actually, how is the differential? We can, in fact, extend to a differential circuit. The benefit of differential is it is not sensitive to common mode noise, therefore we will get better performance. So what is an example of a differential inverter? Because actually differential inverter is the basis of this ring oscillator. Ring oscillator for making clocks, sorry, not here. But we can have differential delay elements also, everything similar according to that. Because if you have a differential inverter, then you can make a differential delay element. So starting from a simple cross-coupled latch, okay. So this is a differential inverter. Actually, it's a cross-coupled latch, right? So because till now, whatever delay element we are talking, all were simple inverter or current starved inverter with single-ended. But it easily can be extended to differential architecture. VI plus, VI minus, VO minus, VO plus. Right? This can be a simple inverter, right? Differential inverter. So MM1, MM2, MP2, MP1. This circuit essentially has positive feedback, right? Because of this cross-coupled latch. What is effective equivalent circuit of this? If you look at the half circuit model, small signal analysis. It is the small signal model of this. Essentially, it shows a negative impedance due to this cross coupling. So effective impedance, if I, instead of connecting gate of MP2 to VO minus, if I had connected to VO plus, then I would have plus 1 upon GMP. Now by making this configuration, I am making a 180-degree phase shift because of positive feedback, therefore effective impedance now will be minus 1 upon GMP. So that's why it is unstable, and that is effectively this is what we want. Effectively it's very fast and it is not sensitive to common mode noise, therefore working with differential architecture is preferred to single-ended architectures in DLLs. So now how to make it a VCDE. So one way of doing that is you just add 2 transistors here. I want to control it, right? So I add 2 more transistors. So this was MP1. So I make 1 transistor parallel to MP1, a simple case. And this is VCTL. This was MP1. This is parallel to MP1, for example, MP3. And this was connected. I don't draw the remaining part. This was VO plus. This is VO minus. And this is VDD. So I don't draw the remaining part. You put MP3 here. Similarly, on the right side, you put a parallel transistor with MP2. Right? And the remaining part will be the same. So now what it does is, effectively if I don't have MP3 and MP4, this will have its own delay, which is very fast in fact because of positive feedback. And it determines by the effective capacitance that I see here. right? This is a differential architecture, therefore it will have a positive transfer function. Means that if I look at VOD will be VOD 0 e to the power plus t upon tau. This is the way it works, right? And this tau is equal to, this is plus. Tau is equal to GMP plus RDS N inverse plus RDS P inverse, the entire thing inverse, into C effective. Right? Which is, I can almost say that it is C effective upon G. So this is for the ideal case, when I don't have any control. Now, when I add this, what we do is, we are adding two, in fact, resistor parallel to this one, negative resistor. Now, if I make it more than this, effectively I'm creating a negative feedback system. However, now I can control the delay, because still it will be a differential amplifier, but it may not have a, no, but still it can have a rail-to-rail swing. If it is almost a resistor and I am changing value of the resistor with VCTL, this node can reach to VDD. When this current is off, therefore this resistor also will have zero drop, therefore I can bring it to VDD. So this is just one simple way of making a differential delay element. So we call it differential voltage control delay. Now, how to use it to make a ring oscillator? In a single-ended inverter, okay, conventional inverter, will this oscillate? Why? Why? Phase shift. This will give 180, this will give 180, then I have 360 degree phase shift. Yes? It is oscillating, but it is oscillating at zero frequency. The reason is its gain is very high. Therefore, it's too high to oscillate. And its actually oscillating frequency is very low. It's almost zero. Therefore, it behaves like a latch. What happens is that if you have a small change here, this change now will get amplified here. So still it is unstable. It's not a stable loop. However, it will be pushed into one of the two extreme cases, because effectively it's like that, it's oscillating at zero frequency. Right. Okay. So now here, there is an interesting point. Here you can just use two stages, because here you have freedom in choosing the polarity, right? For example, connect them like this. Now this will work, because one of them is just like a simple amplifier, and phase shift of these two are not exactly same. Therefore, it is exactly like you have odd number of inverters. Therefore, this will give more efficiency in the design of, I would not call it efficiency, because no, it's not, because then we have more number of components, but it's okay. But then with two stages, we can get a very fast ring oscillator, even answer to your questions. Here, it's possible to get 3 to 4 gigahertz VCOs just in CMOS. And one more interesting thing is, if you want to look, there is a paper from, actually I may have it here. Interested students look, and we may have some questions from that paper in NSEM. Therefore, have a look, and any question, anything you want to discuss more about DLL and PLL, anyway, that 8:30, 9:30 slot is there every day. Okay, so you can come and discuss. Even read this paper. It's a very this paper. This is also from Razavi. No, it's not from Razavi. Okay, but anyway, this talks about a differential inverter. Okay, and even they have used it as a single frequency also, as a sine wave generator. It is possible. Okay, it's a very okay. It is 900 megahertz CMOS low phase noise VCO. IEEE Transaction Circuit and System 2, February 2001. William Shing and Howard Camp. Okay, so this is one of the references. And I chose a simple paper, simple in the sense that simple for you to understand. And with this background that I explained today, I don't think there will be any problem. Phase noise analysis you don't need to do, but if you want, we can also talk about phase noise analysis in this series. See, what is the control voltage? This is VCO, right? Where is control voltage and how does it operate? And whether it is a sine wave generator, is it a square wave generator? So you read the paper, and that's quite, with this background now you have it, is very easy to understand it. They have even done this analysis for one thing just I wanted to add, just to have an idea. So today I told you what was the value in the example. It was a few hundred picosecond per volt as a typical value for the sensitivity. 100 picosecond per volt. See, for project, as I said, essentially, even if we consider this relation was based on this relation, essentially, it's based on considering velocity saturation in devices, which happens in 0.18 micron. However, frequency is linear, but delay is not linear. Okay, so this is just one example in the same technology, but it's not, I think, UNC, it's TSMC. But it will give you just typical values. For example, for effective voltage changing from 580 millivolt to 780 millivolt, the delay changes around from 250 to 850 picosecond. And the slope of this line will show the sensitivity. So as you see, here sensitivity is very high and then it will reduce. Therefore, usually it's better if you want high sensitivity to use this range, if you want low sensitivity to use this range. But anyway, fortunately for the case of PLL, you want a linear relationship with frequency that you will get. Therefore, for DLL design, we usually use some particular range. But for PLL design, you can use the entire range. That is also an interesting result. And interestingly, they have shown that this analytical model and simulation are almost matching. Okay, therefore, now we have 2-3 examples. So DLL loop will be almost single pole if we use a single capacitor at the output. By the way, so we don't need to use RC as we discussed last time, because DLL loop was stable, therefore we don't need to use RC. Therefore, it makes it first order, and then for design parameter, essentially will be just time constant and loop bandwidth. So for DLL design, it's very similar to DLL design, only in DLL design, we are looking at the delay which has a different relation. Now we have this KVCDE instead of KVCO, but loop bandwidth is same as before. However, instead of second order, we have a first order. Therefore, loop bandwidth actually, there we have zeta omega n and zeta omega n and omega n, right? Here we have just that parameter, value of pole, which determines bandwidth as well as latency, direct trade-off. So, and if you are interested, then there are many issues and many things that can be, done as a project afterwards. For example, in clock data recovery, how we extract clock from a data. See, that's a very interesting area, because you cannot transmit. Of course, there are systems that the clock is transmitted along with data, but in many cases, actually clock is extracted from data. Do you remember I asked you this question, if we have a clock and data which are operating at two different frequencies, can we make a DLL? Actually, this is done by using a PLL and an edge detector. Suppose you have two different frequencies and then you want to extract just clock. You want to make sure that you are able, because data frequency is not a constant frequency. That makes it difficult, right? Because it's changing and you cannot always predict how it will be. Therefore, one of the best way is to use edge detector, means that detect edges, because whenever data changes, there will be a clock there, right? So they extract edges and then use these edges, and then there is a lot of mathematics also behind that to extract clock from data. Extracting clock from data is a very interesting area of research, specifically at high bit rates and even for on-chip communication, because you may not want to, when considering a very big size of SoC nowadays, you may not want to transfer clock everywhere. One of the ways which would be appropriate is to just have it and in one place and then extract it from data in other places. And of course, for off-chip communication, that of course is always a point. So to extract data. So this is one of the interesting things which can be done as a project, as an application of DLL. And so overall, we have covered these two parts. I try to make it in such a way that end of March, these two will be over. So then we will start again looking at other topics. So there are in fact many topics. Always I think that, always we should have more and more and more number of courses to cover, more and more and more, or more details. Anyway, so then use this paper as your reference, and then for your project, I didn't see anything on post on Moodle. You can just make a table and then just send it to me. That is also enough. If you don't want to keep it on Moodle, that's fine. You just make a table. Don't use same number of ring oscillator. Okay. See, there are two trade-offs you have in your design. You want to operate it at the frequencies between 40 to 320 megahertz. So either you can change your delay of single stage, or you can change number of stages. That gives enough freedom to have different design. Therefore, don't use same number of stages for ring oscillator. So therefore this creates enough freedom to have different values of delay. Because when you want to generate, say, 40 megahertz, for example, 40 megahertz. So frequency essentially is low, it's not very high. Therefore, this means that either you should use a large number of stages, because to make 40 megahertz at 0.18 micron technology, this means exactly. You have two options. No. Make both different. It's better. See, you have two options. Either use a large number of stages and each stage has a small delay. Or use each stage with a larger delay. So you can estimate. For example, for 40 megahertz, what will be your time cycle? Cycle time? 40 megahertz. your T will be 1 upon 40, 10 to the power minus 6. 1 upon 40 will be 25, 2.5. 2.5 into 10 to the power minus 9, right? 2.5 nano. 25. It is 100. It is 10 upon 4 into 10 to the power. This is 10 to the power minus 5. This is minus 6. 2.5. This is 10 to the power minus 5 upon 4. Okay. I write it 10 upon 4 into 10 to the power minus 6. 10 into 10 to the power minus 6. This is 10 to the power minus 6 upon 40. Okay, yeah. Okay. So 25 nano. Fine. Yeah. Okay. So 25 nanosecond. Now look. This is T. And T is, you have a number of stages. And each stage has a time delay of T. One is for rise, right? One is for fall. So then this is 25 nanosecond. So see how much freedom you have here, and this is a large value. Therefore, TD or TDF are very small. In fact, it's not exactly TD or TDF. Actually, it will be TR and TF. But it's okay. Then when you simulate, you will get the difference. You will adjust it. But then suppose, for example, if you use 21 stages, then say 25 stages, then means that this will be around 1 nanosecond. So 1 nanosecond, to make a delay element with a value of 1 nanosecond. Yeah. Yeah, you can. Fine. So you can use what we suggested. Amount of time, you mean? Entire circuit, you will make the number of stages high. Yeah. A simulation will take time. Fine. You make it, you use capacitor. That's a good suggestion. So essentially it means that you have your delay is the current of current star is determined by this, right? C L upon I. What will be the model? Model is like that. You have C, this is inverter, and here is the current star. VB2 is coming from that mirror. Okay, I'm not drawing it again. So here you can put one CL. This current is I, which is controlled by the bias and will give you the delay. VB is the range of the voltage. And here will be the final output. And this will go to, this is in fact your VCO. Now this will go to the phase detector, right? This is the last stage of this ring oscillator. Then you have other stages and this will come back to the loop. So you can also add capacitors here. Here might be more straightforward. The reason is because here delay is controlled by I. Therefore, you will get a better efficiency of the controlling delay. Here will be the delay of an inverter, and now when you are loading, because this is not exactly linear, but here it is linear controlled by V. So let's see how much will be the value. For example, time delay is proportional to C upon I, CL upon I. One thing also you can do you want to increase frequency if it is too large, this delay? Because that won't affect. Has anybody started design? Okay. So, but I don't think it will affect on the design, right? Because anyway, you are getting right now small delays compared to the value which is required. No, what is your, stage delay? Suppose one stage delay. How much is it? Just one inverter. Without any extra load. 1.1 nano? Okay. 1.1 nano. And of course, this 40 megahertz is the minimum frequency. It's okay, therefore keep it. Keep it. 1.1 nano, it's okay. Because I think if you are getting 1.91, it won't be difficult to get 4 or 5 nanos. And then you can have just, say, 7 to 9 stages. And it's, but see, there are 8, so 8 different number of stages. I don't think there is any difference. See, if a loop is locked, and then we want it to lock to a new frequency, that will take some time. That time is same time we say that for loop to settle to the new frequency. Listen. No. This. No. This is oscillation cycle. You're talking about this, or you're talking about the LL example. This is oscillation cycle. You have a number of stages. Her stage has its own TDR plus TDF delay. So, this is a separating. Just I explained it next time. So, this is delay of one inverter. Current. Okay, so then you keep it as it is, and even if it takes, see, ring oscillator oscillation doesn't take time, but when you keep it in the loop, it will take time. But it's okay. You have enough time. Keep it running overnight. This is usually what we do. But let's have some practical anyway. It may be required to design at this frequency. I mean, this frequency is a very typical frequency. 40 megahertz to 320 megahertz for a clock. Okay. No problem at all. Even you can use HS5. No. HS5 you can run on its own as a standalone tool. That is possible. And it's a very good simulator. Very accurate, very good. Yeah, if only point is schematic link and working with schematic tools in Synopsys may not be so straightforward. One thing you can do, you can generate NetBase by some other tool and then just manually convert it to HS5 format. It doesn't take too much time. And then now do everything, because from netlist onwards, then you can do all simulations in HS5. A1 ways. A ways. It is a part of HS bond. No, it works. It works only in Solaris. Therefore, it will work under Solaris. Therefore, you need a sun machine, huh? Okay, do one thing. It generates text file for the results. You plot it in MATLAB or some other project. That's enough. Because there also you will do similar thing, and then you will just annotate it. So you can do it in any plots, graphics. Okay.